This video is about Bayes decision of point estimations. We consider the case where we have a vectors of parameters. We use the same reference book, Empirical Bayes Methods, second edition, and I consider section 1.6. We start with the notation. X is a vector of random variable. We have p random variable, x1 up to xp. And lambda is a vectors of parameter, lambda 1 up to lambda k. So we have k parameter of interest. The loss function is a quadratic distance between the decision and parameter, as usual for point estimation. And A is any positive definite matrix. And remember, it will be symmetric and invertible because it is positive definite. Then the width, base width is like this, the double integral of the loss function and weighted by the likelihood and the prior distribution G. Okay. Then just like the case where we have only one parameter, what I want to show is very simple. I just want to show that the decision is the posterior mean of lambda. Okay. And I will show you two derivations as in the case with one parameter. So let me talk about the first derivation. First, we minimize the base width to derive the decision, the point estimate, right? So let me rewrite the base width as follows. In the quadratic loss function, I subtract delta G and plus delta G, okay? For both terms here. And then I can split this quadratic term into three terms, okay? So then in the second equality, we have two quadratic terms and one cross product term, okay? Let's consider the first term. The first term is surely bigger than or equal to 0. It depends on whether delta equal to delta G. And the second term is the cross product term. It will be important, but let us consider the third term first. The third term is exactly the base width for the delta G. Remember, delta G is our decision, okay? Delta G is the optimal decision. And it is exactly the base width for delta G. And we know that by definition, the base width for delta G should be the lower bound of the base width, right, for general decision. So in order for this claim to be whole, we need the second integral. That means second integral, the cross product term, to be 0. So let us, just like the case in the previous video about point estimation with one parameter, we set this integral equal to 0, and it is very straightforward to derive the following conclusion, okay? So because the arguments are the same, I don't write down the argument once more, but very simple. Just set the second integral to be 0. Then the immediate condition is delta G for any value of x is equal to the ratio between these two integrals. But what is this ratio? This ratio is exactly the posterior mean of delta, okay? So very straightforward. And then let me show you the second derivation by using calculus. First, I try to interchange the orders of integration. Okay, I put the integration over lambda inside. Then I use a red color parenthesis to highlight this term. Okay. So in fact, after changing the order of integration, we know that it is the expected loss for any given value of x. So that in fact, we can use calculus to minimize this inner integral. Then we can get the optimal decision of point estimate. And remember, in orange color, I try to refresh your memory, and in the orange parenthesis, this is the posterior probability. And then I take derivative with respect to delta. and then set it equal to 0, then we get this equality. Okay, the important thing to notice is A is a positive definite matrix, so it will be invertible. So when we set this thing equal to 0, in fact, it is quite interesting. The optimal decision delta G, as usual, equal to the posterior mean of lambda, but it is independent of A. So it is a interesting remark. Okay, so for any positive definite matrix A, we will get the same decision. Okay, it will not affect our decision.